Welcome everyone to today's webinar. My name is Ian Trevoranis. I'm the Product Line Manager for HORIBA's particle products here in the United States and in the Americas. I'll be hosting the webinar today. If you have any questions, please type them into the chat box. Our presenter is Dr. Jeff Bodycomb. He's our Product Manager for basically everything nanoparticle and a few other things. And he'll be speaking to us today about method development concerns for dynamic light scattering measurements. So without any further ado, Jeff, please begin.
Okay, well, thank you very much. And as Ian said, I'm Jeff Bodycomb, and I'm happy to be here talking about method development for dynamic light scattering. And I'm, as you know, with HORIBA Scientific. So today we're going to talk about a very, very brief introduction to dynamic light scattering, and then talk about the different steps when you go to prepare a method, which would be preparing a suspension, how you filter and clarify the suspension, a few comments on choosing the sample cell, concentration, duration of measurement, and number of repeats. So I'm going to make some comments about each of these areas, and all of them are things you should think about when you want to prepare a method that you might move into quality control work, for example, or if you have a big series of samples. So to get you oriented, let me mention that I have my usual graph of particle diameter here from about 1,000 microns down to 1 nanometer. And we really are working in the range of about 1 micron to about 1 nanometer. And that would be dynamic light scattering with the SZ100. So things you're looking at are things like suspensions or macromolecules in solution. Often you hear the word colloids thrown around, or nanoparticles is the big term now. As you go to larger particles, and even into the colloidal particles, you can also use laser diffraction, which is another technology we offer, but not the topic of this talk. Once you move into particles that are well over a micron, you start thinking about using microscopy, such as the PSA 300. But once again, we're going to focus on dynamic light scattering today. So one key thing to keep in mind is that particles in suspension undergo Brownian motion due to solid molecule bombardment. And really in dynamic light scattering measurement is a measurement of this Brownian motion. That motion is random. It's related to particle size. Small particles move more readily than large particles. Related to viscosity, and related to temperature. And this relationship to viscosity comes up when you think about temperature and when you make a measurement. The random motion is important because when you do the calculations, you assume your particles are what are known as freely diffusing. And if they're not, you'll see results that don't make sense if you interpret them in terms of size. Now the optical arrangement is to have a sample. So this is more or less a top view. So you have a sample in a cell here in suspension with particles. You'll shine a laser light onto the sample here, and you look at the scattering as a function of time at a single angle. Most often I choose 90 degrees, and so-called right angle scattering. You can also use back scattering. That's also available in the HORIBA instrument. Now, why do you want to use dynamic light scattering? It's a non-invasive measurement, so you get your sample back. It requires only small quantities of sample. You can use as little as 10 microliters of suspension, and the suspensions can be fairly dilute. It's good for detecting trace amounts of aggregate. So if you have a suspension of particles and you're concerned that some of your particles are beginning to aggregate and that aggregates will give you trouble, dynamic light scattering is a great way to find them. It's a good technique for looking at macromolecules. So you'll use it when you look at things like proteins or polymers. Now, what is hydrodynamic size? Dynamic light scattering gives the diameter of a sphere that moves or diffuses the same way as your sample. So you'll often hear people talk about the hydrodynamic size from dynamic light scattering. And really, what it means is if you have a perfectly spherical hard particle, the hydrodynamic size is equivalent to the size of the sphere. But what if your particle has two parts, an inner core that let's say is metallic, and an outer shell that let's say is a synthetic polymer? You look at this under an electron microscope, you'll see the metallic core, but because there's no contrast, you will not be able to see the polymer shell. When you examine this particle by dynamic light scattering, you'll actually measure this entire species. So that's quite convenient. Another point is if you have an aggregate. So if you have a whole bunch of particles that are stuck together, and you might look at these by X-ray or microscopy and say, oh, well, you know, I have a little tiny particle that's just this big. But when you put them in suspension and these five are moving together as a group and do not break up, the size you measure is the size of this aggregate. And so some of the things you might do in preparing your suspensions is to break up these aggregates. Finally, let me comment that most nanoparticles you don't expect to be perfectly spherical. And what you get as a hydrodynamic size is really the diameter of a sphere that moves the same way as your particle. So if you have, say, an ellipsoid of revolution like this, you don't measure one of the axes or the length or anything convenient. What you really are measuring is some mixture of these two numbers. Regardless, it's a good measure of size even of particles like this, because as the particles get bigger, the hydrodynamic size also increases. You can make the measurements with the HORIBA SZ100. It's a single compact box that performs size, zeta potential, and molecular weight measurements. So it's quite nice. I like it. So before you put your samples into this magic box, you need to prepare the samples in suspension. And so we have a graph from one of our classes on particle size analysis, our boot camps, where we show percent error as a function of particle size. And generally the instrument error is a fairly small fraction of your overall measurement errors. When you have, then you can have errors due to sample extraction. So you imagine you have a giant bucket of particles and you take out some of the particles and measure them. If the sample of particles you take out is biased, then you will have a measurement error, and that error tends to dominate for larger particle sizes. Now if you have the same bucket of particles and you pull out some particles and put them into suspension, your particles may clump up to even error in size. You may apply too much energy and break the particles, although that's unlikely with nanoparticles. And so your sample preparation errors begin to dominate as the particles become smaller. And this is really because of the larger surface area of the small particles. And so this really illustrates the need to consider preparation of suspensions. So what are some strategies, or how do you think about making dispersions? Well, if you have a dry powder, your problem is a little bit tougher. You have to decide which liquid that you want to put your particle into. You don't want to put your particles into solvents. So if, for example, I have polystyrene latex and I put it into DMF, I could wind up looking at something quite different than what I think I'm looking at. That's because the DMF will dissolve polystyrene quite nicely and take those latex particles and more or less separate them and swell, at the very least swell them, and quite likely separate them. You need to find a way to make the powder wet, and what I mean by that is that you need the liquid to be in intimate contact with the particle surface. You might need some dispersing aids to avoid reagglomeration. So if you have particles and they're wetted, you want to make sure they don't decide to stick together anyway, even though the liquid's trying to move them apart. And you might need to feed in enough energy to break up these agglomerates into primary particles. Now, often this is ultrasound for nanoparticles. Now the mercy in this is that unlike formulations, say for pharmaceutical work or something like that, we don't need to have a really, really stable suspension. We just need it to be stable long enough to get off to make our measurements. Now, if you have if somebody hands you a bottle of liquid containing nanoparticles, so it's already in suspension, life is a lot easier. Now you really need to choose a diluent or liquid that will keep the particles in suspension. You need to worry about a lot less about energy. A lot less about dispersing aids or wetting. You may need to add energy, particularly if that liquid's been sitting around. But again, it's going to be a lot less work than for the case of a dry powder. So I mentioned particle wetting. And so really what we need to have happen is we need to lower the surface tension so the liquid will adhere to the particles. So I have a particle like this, and I have a liquid, and it forms these droplets on the top. It doesn't wet the particle surface. And we have a large contact angle. We'll have bad wetting. I'll have little air pockets fitting around here, which will affect my sizing results. And the real goal is to really completely coat the particle with liquid, like we show here. Now you can do this by adding things to your suspension. Tetrasodium pyrophosphate is popular, any surfactant. Now, how do you check for wetting? Well, what you could do is just sprinkle the particles on top of your target dispersant. If the particles float on top and do not penetrate the water surface, they're not wetted. This is usually a bad sign. So here you can see a beaker, and this is filled with water. And I forget now what I put on top, but I put a little bit of powder on top, and it just clumped up and sat up there, being held up by the surface tension of the water. So I knew that I was in trouble. I took a second beaker, and I put in water with 0.1 weight percent TSPP, tetrasodium pyrophosphate, and I sprinkled a few particles on, and the particles formed this plume, and you can see they just start sinking down and spreading out through the liquid. And so that made me feel quite good, and I said, okay, well, now I know how to wet the particles, and so I am partially on the way to really getting a good measurement. There is one more way particles will get to the bottom of your beaker. If they're so big that gravity is stronger than the surface tension, they'll fall to the bottom. So you can take a rock and just drop it to the bottom of the beaker without any difficulty. If you have rocks like that, dynamic light scattering is probably not your preferred technique anyway. Now, keep in mind that you don't have to work with water. First, I love water. I swim in it. I drink it. It's safe to work with compared to other liquids. And so, that's generally where we start. But don't forget there are other less polar solvents, such as isopropyl alcohol. You can move over to organic solvents like toluene, dimethylformamide. And in dynamic light scattering, the volume of liquid is generally small, 2 to 3 ml at most. And so it's a lot easier to work with organic solvents than when you're using laser diffraction. But keep in mind that they are more difficult to handle, and they pose safety hazards that you need to address explicitly. Now, what liquids or what surfactants do you want to use? Well, check the literature on the web and see what other people use. So, for example, if you have the lead particles, you might just type into Google lead particle suspension and see what comes up in terms of either articles or even the search text. I found out somebody made a lead particle suspension in MEK. Well, that tells me that I ought to be prepared to try some MEK with these lead particles and see if it's going to work. So you get a lot of great pointers. Also, try a series of options. So here I made a series of suspensions, and I just took 20 ml scintillation vials, filled each with different liquids, put some particles inside, looked at them, decided do they wet. This one, well, one of them didn't wet at all, some of them wet quite nicely, and then I can make measurements on the ones that look best. Now, surfactant addition is not simple in the sense that if little is good, more is not always better. If you add too much surfactant, you can see materials re-agglomerate. So here's a sketch of this concept. You measure particle size, and the particle size with no surfactant is really huge because it's still agglomerated. And then the measured particle size drops down to something civilized and keeps going down. And then I add too much surfactant, it begins agglomerating again. Common concentrations are 0.01 to 0.1% surfactant. So if you are worried about this effect, you can make some measurements of this measured particle size as a function of surfactant concentration. Fortunately, most of the common surfactants are reasonably forgiving, and so when you make measurements, you might measure at 0.01, 0.02, 0.04, and so on in concentration, not a logarithmic scale, not a linear scale. Okay, ultrasonic energy ultrasound is used to break up agglomerates because it's a nice way to put a lot of energy into a system. So you make little microscopic bubbles and they collapse, and it creates this big shearing action which agitates the liquid and the particles. This breaks apart agglomerates. In some cases, fragile particles are shattered. It doesn't happen very often with nanoparticles unless you add a lot of energy. And the selection of the appropriate type and level of ultrasonic energy needs to be made reasonably carefully. Now, one thing you might notice as you use ultrasound is it heats the liquid up. So if you're really putting a lot of energy into a sample, you might want to put it in an ice bath before you put your ultrasonic probe into your sample in order to take away the heat, because these ultrasound, which is really energy, is being converted to heat in your sample, and that may not be good for the sample. There is an optimal range of energy. So here I plot aggregate size as a function of increasing energy. So as I add energy, my size goes down, it becomes flat, and if I add too much, it begins to break up the particles more. You really want to just apply enough energy to get somewhere in here to break up the particles. If you start damaging your sample, you don't know whether you have smaller particles due to changes in your preparation process or changes in your ultrasound. So if you get to here, it could be confusing when you're trying to use light scattering as a diagnostic technique. Okay, filtration and clarification basically comes about because large dust particles scatter a lot more than nanoparticles. And so you really need to do something about getting rid of these extra impurities. So what is dust. Dust are the large, rare particles in the sample. They're generally not really part of the sample. So to twist an expression slightly, they're kind of the elephant in the room. You know, now, why would I think about elephants? Well, I can imagine an African elephant weighs about 3,000 kilograms, and a praying mantis weighs about 3 grams. And so a praying mantis is the largest kind of bug that goes through, eats other bugs. So there's about a 1 million time difference in volume, assuming each animal has about equal density. So that's the same difference between a 10 micron dust particle and a 10 nanometer nanoparticle. So you can imagine, if you have a herd of elephants along with some praying mantises, you're not going to notice the praying mantises. So the bugs are just going to be dominated by the large beasts, even though numerically they're more of the bugs. So what do you do? To push the analogy beyond breaking, you can use a fence to keep out the elephants. In our case, the fence is a filter with nano-sized pores. So what are some ideas when you're filtering samples? If the sample has large particle contamination and the particle is small enough to pass through a filter, then filter the entire suspension. So going back to my example of, let's say, 10 nanometer or 20 nanometer particle, you might filter the entire particle suspension through a 100 nanometer filter. Now your small particles pass through the filter quite nicely, and your large particles are caught up in the 100 nanometer filter. If you do decide to filter a sample, be a bit careful. Filtering can remove large particle contamination that is important. So you can imagine, going back, if someone brings you a bucket of stuff and they want to know the size, before you filter out the large stuff, figure out if the large stuff is really relevant to your results. Try and choose a filter with a pore size twice the size of the large particle of interest. Sometimes what you can do is you can filter a sample through a 0.1 micron filter, look at the result, then filter through a 0.2 micron filter and look at the result. If your result is exactly the filter size, or if the filters are becoming plugged, then you'll know that your filtration is strongly affecting the sample. I like syringe type filters and carry them around. Recommend them to everybody. They introduce less dust from the outside. So you load a syringe up with liquid, you put the filter on it, and you push the liquid through, and it drops right into your cuvette, and there's no more chance of contamination. Now they tend to come in 2 diameters, a 10 millimeter and a 25 millimeter diameter. The 10 millimeter diameter is less expensive. It's good for small volumes, and there is less filter holdup. So if you ever filter a series of samples, the 10 could be helpful, or if you have only a small amount of liquid. The problem is they tend to get plugged up faster, and so you can't use them as long. The 25 millimeter diameter, it's a little more expensive, has more holdup, but you can use for larger volumes. And so when I go and filter 10 ml of a diluent, like a salt solution for measurement, I'll use a 25 millimeter diameter filter, and I'll use the same filter for the day. If I have a series of samples to filter, I'll use a 10 millimeter diameter filter, just because they're less expensive and I'm going to throw away a lot more of them. I don't need to filter as much material. Now, what about choosing filters? There are a lot of different materials available. So this is a little sketch from Wattman. They have nylon, polysulfone, Teflon, PVDF, polypropylene. They're Anapor, PES, CA, RC. And you can read the application guides to see which materials will work for your application. So if you're filtering an aqueous suspension, you do not want to use PTFE, Teflon, because the water does not wet the PTFE, and you won't get anything through the filter. You'll start looking at something like nylon or the anapore. Now, the anapore is most widely useful, but I think it's one of the more expensive materials. So you want to pick something based on what's compatible with your sample. PTFE, by the way, is good if you're working with something like toluene or THF. So someone asked, what is anapore chemically? I think anapore is a ceramic type of filter material. That's all I can remember offhand. Pay attention to price. If you're running the same sample over and over again, you can save everybody a lot of headaches by choosing a less expensive material that still works. Okay, sample cell choice. This is something that you should keep in mind, that you have options. So first, you can pick your materials. Plastic is great because it's very inexpensive and disposable. It's a little weaker because it's not very chemically resistant. So generally you use plastic when you're working with water. Glass is more expensive, which means you're stuck washing glassware. And so that's part of using glass. But it has the advantage of good chemical resistance. So if you're working with THF or toluene, you'll wind up washing glassware because you'll use glass sample cells. Cell volumes range from 10 microliters on up to about 3 milliliters. As the volume gets smaller, the cells become more expensive, they become more difficult to clean, and you need less sample. In general, I recommend you use the largest sample cell size that works for your application. There's no reason to use a 50 microliter disposable sample cell when you can use a 3 milliliter disposable sample cell. The latter is less expensive. Okay, concentration. Now, when you're dynamic light scattering is very forgiving in terms of the concentration of nanoparticles that you use for measurement. But there are limits. So first, if the particle concentration is too low, your data will be noisy. You just don't have enough particles in there scattering. You also have a problem because the nanoparticles may give much less signal than your large particle impurities or dust. So when your particle concentration goes too low, you get a lot of noise on your result. There is another effect for extremely low particle concentrations where the statistical relationships inside the math don't work. That usually is not an issue. Now, all the theory, except for the statistical parts, assumes near zero concentration and zero particle-particle interactions. Sorry about the straight parenthesis there. And what that means is that most of the time, you cannot get to too low a concentration. So I have this in here for completeness. Generally, the lower you go, the happier you will be. If the concentration is too high, what you'll have happen is something known as particle-particle interactions. So if you have simple hard spheres, they'll start to collide, and so they won't move freely, and the equations don't work properly. There's also a phenomenon known as multiple scattering, where scattered light from one particle strikes another particle, and that's scattering from that second particle strikes another particle is scattered again before it reaches the detector. That also distorts measurement results. Now, particle-particle interactions, of course, persist no matter what you do to your optics. There are some arrangements that get you around multiple scattering in the SZ100, but because of this, I tend to prefer working with dilute suspensions. So here's an example of a sample that I ran recently, where I made a plot of the z-average diameter in nanometers. You can see this is about 1 micron. And then the concentration in parts per million. And notice this is a log scale. So I'm not making 3 ppm, 4 ppm, 5 ppm steps, or so many small steps. I jump from 3 to 11 to 30 to 60 to 100 to just about 1,000 parts per million. The lowest concentration, I have these error bars set as the standard deviation of repeated measurements. You can see that the standard deviation became quite high. So I didn't like that because there was too much noise in the result. As I increase the concentration, then I see really a flat spot in my curve. So these all have about the same measured size. Now we get to this higher concentration, you start to see this measured size go down. Now the size of these particles is not changing. So what's changing is the measured size of the particles. So when I go to make measurements in the future, I'll tell people, well, look, make your sample between 15 parts per million and 60 parts per million, which is a pretty wide window to work with. So, a 5 to 1 range. The tails of a distribution have an effect on this results of this kind of plot. So now eyeballing it. You're in the lab, you need to make a measurement, you need somewhere to get started. And so I took some pictures of this sample. Now this material is about 1 micron. And I show these are the sample cuvettes. I put some paper behind it. And you can see that the best range of concentrations for this material ranges from just a little bit cloudy up to somewhat more cloudy. Once it gets to milky colored, it's too concentrated. So I would tend to I probably would have started somewhere around between here and here if I knew nothing about the sample to make the first measurement. Now earlier I mentioned particle-particle interactions versus multiple scattering. And there's actually a way you can turn particle-particle interactions on and off in a charged particle system. And that's by adding salt. So if I take a nanoparticle and I dilute it in DI water and the material is charged, then you'll have quite long-range interactions. But if I dilute it in salt water, here I use 10 millimolar sodium chloride, then the electrostatic interactions are suppressed. And so what I've done is I've basically turned off the particle-particle interactions. And I've kept everything else the same. I have the same optics. And so we can ask how much of this distortion we see with concentration comes from particle-particle interactions and how much from multiple scattering. So on the left, I plot the measured z-average diameter or size, again as a function of concentration. Now notice that this is much smaller. This is only 30-odd nanometer size, and my range of concentrations is higher because I wanted to get a nice strong scattering signal for this plot. Now the red, you can see that the measured size just changes constantly with concentrations, just consistently going down over all the concentrations I measured. And so the range of sizes I see between this bar and this bar is quite wide. But when I dilute, instead of using DI water, if I use sodium chloride, and I've turned off the particle-particle interactions, the measured sizes fall into a much more narrow band over this range. And we can get into a discussion about how much of this curve is really due to experimental error. And the answer to that would be a noticeable amount of it. But all these numbers fall into a very narrow range, and it's only at the highest concentrations that the measured size decreases. So what this tells you is if someone comes to you and says, oh, this is because of multiple scattering, well, no matter what you do, you're going to see this effect. What this kind of effect is really due to are particle-particle interactions. And that points to the importance of thinking about your chemistry and suppressing charged interactions. Now, the reason I know this material is charged, of course, is that I use the SC100 to measure the zeta potential of the sample in DI water, and it was quite substantial. I think it was minus 40 or minus 50 millivolts. And so, when I started all these measurements, I knew that I kind of predicted this effect. Now, once again, let's go back to eyeballing it, because you don't. So you'll make a sample. Now these are much smaller particles, so you can see the suspensions are much more clear. And the best range of concentrations goes from clear to just slightly cloudy. And so if you have an unknown, you're looking at something between clear and just slightly cloudy as the best starting point for your measurements. Now once you have a measurement from a sample, any concentration, you know how to set up a concentration study if you want to develop the method further. Now, measurement duration, there are a couple comments here. The first is I mentioned temperature before. If you take a sample from a 23-degree laboratory and you put it into an instrument that's set to 25 degrees, then you really need to wait 3 or 4 minutes for the sample to get to the same temperature as the inside of the instrument before you make your measurement. So you have to reach a thermal equilibrium. And that's because Brownian motion is dependent on temperature and, more importantly, viscosity, where viscosity is a stiff function of temperature. One way to make sure that this process is quick, and generally the best way, is to set your temperature, your instrument temperature, to match your laboratory or your sample temperature. Now, how long to measure? Pretty typical is 1 to 2 minutes. If you're getting noisy data, you might wait for maybe 5 minutes for a measurement. So the technique is fast, and one of the nice things about having dynamic light scattering in your lab is that you can go out and check some effects very, very quickly because it's such a fast technique. In fact, most discussions we have around running a sample comes down to, well, let's put it in the machine and see what happens because it's faster than theorizing. Well, how many repeats? Well, 3 to 6 is typical. So I'll run 3 repeats. If I want a better idea, I'll go up to 6. And there's real basis for that. So if you start thinking about the confidence interval on a mean, and I assume a normal distribution of results, which is a bit of a heroic assumption, but it makes the math easier. It's the t-value times the standard deviation over the square root of the number of measurements. So the confidence interval over the mean of a distribution is t times s over m divided by square root n. So s over m is really your coefficient of variation times t divided by square root n. So for 90% confidence intervals, then I have a table with n, with t over square root n, that's this ratio here, and I figure a coefficient of variation of 5%, which is something that ought to make one happy in dynamic light scattering, times t over square root n. I can say, well, my error bar is going to look like 22% for 2 repeats. Well, that's kind of huge. Once I get to 3, it's 8%, which is getting respectable. And 6 repeats is down at 4%. And so that's a very respectable result where you can sit and be happy with the answers. So that's really the basis behind choosing the number 6. A little bit of force of habit. Some people might say 5 is more optimal. You save a little less than 20% in your time, and your error bars are around 5%. Okay, well that ends the lecture part of this, and so I want to move on to questions and answers. And if you find a question later on, you can always send the questions in to labinfo@horiba.com. Keep an eye on our particle email newsletter so you can hear about more webinars and announcements, as well as materials we write on these topics. And visit the Download Center online to find this video and slides from the webinar. Okay, thank you very much.
All right, thank you, Jeff. As he was saying, now is the time to send in any questions that you've had that have come up. And I have a more exact answer for what the chemical nature of anapor is. It's actually aluminum oxide, according to the Whatman website.
Aha, okay. Thank you.
Dongmei, and I hope I'm pronouncing that correctly, is asking what material you use, Jeff, for the concentration study.
The first one, I forgot what was in the first one. So that 1 micron stuff, I forget what it was. Sorry. The stuff at the end was a silica. So, and those charge effects that you saw in the silica are quite common for nanoparticles. So most particles in suspension stay in suspension because they repel each other by a charge on the surface. So if you think of 2 nanoparticles, when they contact, they have a large surface area. They contact, the surface area goes down. So they like to stay together and flocculate. So you want to prevent them from colliding. So when you do formulation, what you'll do is you'll charge up each of the 2 particles, either by manipulating the particle surface or manipulating the pH of the suspension, so that they stay apart quite nicely. And that's great for keeping them apart. You want to weaken that effect when you're measuring size. And of course, you can monitor that effect by measuring zeta potential. And that's the topic of a different webinar.
Okay, Johannes is asking, do you have comparisons of particle size diluted with centrifuged aliquate, maybe aliquot, versus DI water and 10 millimolar sodium chloride?
I do not. And so I think what you want to look at, all right, so if I centrifuge it and you're saying use the supernatant to dilute, I'm looking for the question.
Yes, that's what he's saying.
I have, yeah, okay, I have not done that. In fact, the suspension I started with only had a little bit of salt.
Okay, Lou is asking, what standards do we recommend for dynamic light scattering?
What standards? I wander around with Duke Scientific 100 nanometer PSL. If there's a, first time I see a machine, I stuff that in the machine and see if I'm getting a reasonable answer.
All right. My doppelganger is asking, how long does it take to reach equilibrium before taking a measurement?
Usually a couple minutes.
And is there any indicator as to when that's ready, or is it just kind of a rule of thumb?
Kind of a rule of thumb. And well, I'm sorry, that's not quite true. The easiest indicator is when you look at the you make a series of measurements, and so I make 2-minute repeats. And if I'm too hasty in starting the measurement, the first measurement will be a little bit away from the average. And so usually what I do is I press start and ignore the first, just to get a sense of what's going on, I ignore the first result.
All right. That looks, oh wait, no. Yvonne has asked, what's the best way to take into account the refractive index and its imaginary component? Do you measure this in the lab, or do you use a reference value?
Well, I'm in a happy world of nanoparticles where I don't have to worry as much as laser diffraction. Yvonne, when particles are quite small, refractive index effects become much weaker And so what happens with nanoparticles is that you use a close enough estimate, and that works. This is different from laser diffraction. So as your particle size goes up and your light is spending an appreciable amount of time inside the particle from the point of view of the light, then refractive index effects become significant, and that leads to all the questions of laser diffraction. We can escape that and use reasonable approximations and be happy. Okay.
Dongmei is asking also, should we always centrifuge to concentrate very low concentration samples? For example, a situation where the total solids are less than 5 mg per mil. Or, I'm sorry, 5 mg per liter.
5 mg per liter.
I'm going to hope that's a typo.
Well...
5 mg per liter, yes. Centrifuge, please.
Yeah, I mean, yeah. Now the hazard in that, is that when you try to centrifuge a nanoparticle, you find out that it takes an awful long time for them to actually get to the bottom of your centrifuge tube. Okay, and I see there's a question.
The flip side, of course, is that if you don't have enough scattering, and yeah, exactly. If you don't have enough sufficient particles or macromolecules in the scattering volume, you won't get a measurement period. So in that case, I would imagine you'd always centrifuge, regardless of the pain involved.
Yes. Okay. Yeah. Although okay. See, how do you select your diluent? What basis do you use? So when I select diluent, I try to find out as much as I can about the chemistry and specifically the surface chemistry of the particle. So I need something that's compatible with the particle that won't dissolve it, and I need something that wets the particle. And so really those are two questions I want to answer. I see also someone asks if they can use IPA to pre-wet a PTFE filter, then use water. I don't know. I just use nylon or Anatops. So maybe a fun thing to try someday. But I don't think it's worth the effort.
Okay, well that looks like it's the last question. I'd like to thank you, Jeff, again for giving us the presentation today, and thanks to all of you in the audience for coming to attend. This is our first webinar of 2013, and it certainly won't be our last, so please be on the lookout for our monthly newsletters and our webinar reminders. And if you have any ideas of your own that you'd like to share, or perhaps data that you'd like to present, please do drop us a line at labinfo@horiba.com, or you could email Jeff or myself directly as well. This webinar was recorded. Usually we can get it up on the website in maybe 1 or 2 business days, depending on the holiday schedule in Japan usually. But it will be up on the website. It will be coded as TR014. It's in the training section. And I hope you all enjoyed today's presentation.
Yes, thank you very much.
Thanks, everyone.
Okay.
Have a good day.